photos, but maybe this will be the third time this video fails. Alright, so multi-dimensional momentum. Best example of this, I think everybody has seen, is playing pool. Right? Many people play billiards, okay? Billiards. Alright? For instance, we had a debate in my other class about what would be the best shot for the one I drew. But, you got this pocket, that pocket, this pocket, and this pocket, right? So let's say, oops, what have I done? That's not a pocket. Alright. So let's say you got the 8 ball about here, right? And the cue ball is hanging out about here. And you want to win. You're about to sink that 8 ball and try to win. Which pocket are you going for?
The middle one.
Side pocket? Yeah, that's the one I would go for. The other class was saying go for the corner pocket, but that being farther away, it's a smaller target. If you're off, it's easier to miss them. I always love the side pocket shots, right? And the way you do it is you want to hit the 8 ball right there. Imagine you drew a vector through the 8 ball into the pocket, right? Wherever that vector comes out, that's where you want the cue ball to hit. So the cue ball is going to come in, hit the 8 ball right about there. Now, the 8 ball is going to fly that way. Here's the cue ball coming in, right? Which direction is the cue ball going to go? To the right? Just keep going straight?
Down to the right.
Okay, down and to the right. Right? Now, it does that because momentum is conserved. And remember, momentum is all about forces, right? So when this hits here, cue ball experiences a force that way, down and backwards actually, right? So it's gonna have to slow down its x velocity a little bit and give it a little y velocity, right? So a couple bits of terminology here to get you started. This is the incoming ball, and we say that the incoming ball is deflected off of its path. We say it gets deflected off of its path by a certain angle theta. We would actually call it a deflection angle, right? So when a ball is moving and hits something else and changes its path, it's been deflected. This one initially stationary, it's the stationary one. But quantitatively here, what happens is the total momentum before the collision still has to equal the total momentum after the collision. But the way we calculate it is in the x and y direction separately. Now, did you cover multidimensional momentum in AP Physics 1?
Yes.
No? Okay. We definitely don't in AP Physics, or in Physics 11H, but it's really not that hard. You might remember previously saying, on the regions they say P before, the symbol for momentum is a lowercase p. P before equals P after. That's how they say it. You could say it P1 equals P2, PA equals PB, whatever you want to say. A and B is a little bit weird because you think A after B before. So usually you'd say 1 and 2. But then if you have objects 1 and 2, this gets kind of crazy because the subscripts and the symbols and variables you're going to use here. So, you got to be organized, but don't get too hung up on the tiny details. So what we do though here is rather than just saying, you can say Px before equals Px after, and Py before equals Py after. That's what we end up saying here. So the horizontal momentum, or the x momentum before the collision, must equal the total x momentum after the collision. So what happens here is each one of these pool balls here has a little we think of it like vector quantities, right? The x momentum of the 8 ball plus the x momentum of the cue ball added together must equal the initial x momentum of the incoming cue ball. All right? Now, the y momentum here, this is often the case, is it has to be 0, the total y momentum, right? Because our initial cue ball here has no momentum relative to the y-axis. It's just moving in a straight line. So when this one comes in and hits, the upward momentum of the 8 ball has to equal the downward momentum of the cue ball, right? You want to be careful here because, look, what if, if you hit this too fast, and you send this flying too fast that way, the cue ball could end up rolling into the corner pocket, get scratched, and you're going to lose this game, right? So there's different things in pool, right? You put a little backspin on that. You ever learn how to do that, because that'll get that cue ball to stop once it hits that 8 ball. And the 8 ball gets shot over. Or you just, don't do it too hard. You hit it into the side pocket. There's lots of examples of different multi-dimensional motion. Multi-dimension momentum conservation out there. One of them is explosions. Right? Something starts at rest. So the two carts, right? You put the little spring in, then you click the spring, and they fly off of each other, right? That's an explosion. Throwing something. If you're at rest, if you're on rollerblades, like really good rollerblades, and you throw something heavy, you roll backwards, right? You push off the object, that pushes you backwards. The ball goes forwards, right? Just like that one we talked about with the throwing the wrench. Did we actually go over those? I don't remember. We haven't gone over this. Made a video for it. No? Yes? I don't remember. Alright, after this I'll check. Alright. So when something explodes apart, for instance, the example we use, one of the ones we're going to do here is a firecracker molded into something. Just kind of silly thing. All right, so you've had some air pocket or something, right? And it spontaneously exploded into 3 equal mass pieces, right? M1, M2, and M3, and they went flying out. Well, the total x momentum and the total y momentum would have to be conserved. So that these would have, if they were the same mass, they all went flying at the same speed, they'd have to be the same angle between them all, 120 between them all, to make sure everything is balanced. Then you kind of go from there, okay, if one is less mass and one's faster, then you can go ahead and figure out a lot of other stuff. One of the videos I showed in class yesterday, I'm not going to record myself showing you this, but I'll show you the video after this, is nukes in space, all right? So we've blown up thousands of nuclear bombs on the Earth and in the Earth orbit / in the stratosphere. Just way too many. I'll show you a couple pictures here in a second. But the nukes in space one's interesting. They go way, way, way to the upper atmosphere and they detonate them. Mostly to test it, really, just to see what would happen. I mean, they had ideas, but they didn't fully understand the long-term health effects of all of this stuff, increasing the background radiation levels of the Earth. Not a good thing. But what they did, they launched them, and the explosions are very surreal. They look kind of like, like a Star Wars. I mean, it literally is a sphere, the explosion. And it's because of the lack of a lot of oxygen, you don't have the big fireball. It's like an electromagnetic ionizing glow effect to it. It's really pretty interesting, but it's symmetric. It's like it's a ball because of conservation of momentum. It's interesting. Anything that decays radioactively, this is pretty cool. Like something that undergoes fission, right? If you have an unstable nucleus and it gives off an alpha particle or something, right? The nucleus recoils. It moves backwards a little bit. So even when something launches out light, if it was a gamma ray, right? If a shot an alpha particle that way, a gamma ray that way, well, it would recoil. Even shooting out a photon, light, it recoils. It's pretty neat. So recoil, that's another little bit of terminology, kind of like deflect. Recoil is when something heavier shoots something light, and the heavier object goes backwards a little bit. Moves backwards, the recoil. Actually, I can show you an example of that as well from the same source as Nukes in Space, the atomic artillery gun. They really got creative with that stuff. They made they made a shoulder fire nuke called the Davy Crockett. No joke, the Davy Crockett they called it. And they were testing it in Hawaii. They had soldiers testing, firing, and practicing. And one of my friends, he works for the Army Corps of Engineers, and there was this old lava field, and it started setting off radiation detectors. And what it was the people were training to shoot these shoulder-fired nukes. What they used to simulate the actual warhead was something that was loaded with depleted uranium because of the density of it, made it heavy enough so they could learn how to shoot it. And the depleted uranium is still radioactive. And it was starting to get a large concentration of it. There was a large we weren't still testing it, but there was a large concentration of this depleted uranium in this field. So what they did was, they took a helicopter, they made a thing on the bottom of it, like a support system. They hung different radiation detectors on the bottom of it, and they flew across this lava field. It was the rocks, not actual lava. They flew across it back and forth, and they mapped the radiation. They were able to pinpoint where these pieces of depleted uranium were. They went back and then cleaned them up. But fascinating stuff. I'll show you those couple video clips now.